Hi everyone! We have a pretty good start on exponential functions, but what we want to do now is introduce them into the fold of our parent functions and deal with them in a lot of the ways that we've dealt with parent functions. So one of the big ones is having a parent graph in your head and being able to apply transformations to it. So in this video, we're just going to work on the parent shapes, and exponential functions are unique somewhat to the way we've dealt with parent functions in that it's not just one function, it's all of the exponential functions. So we want to add 2 to the x and 3 to the x and 4 to the x and 5.7 to the x and 1/2 to the x and 0.1 to the x, all to the list of parent functions. This is somewhat similar to the looking we did at power functions, but we didn't add all the power functions into our parent function list, just very specific ones. So we have an x squared and an x cubed, but we didn't really add x to the 4th and 5th and 6th and 7th. However, we did look at those to see how they were similar to some of the other shapes that we do work with. So that's more like what we'll do here. So I'm going to do 2 to the x and 1/2 to the x, and then I'll talk about how we want to kind of generalize this in our head a little bit. So let's start with y equals 2 to the x over here, and I will work on y equals 1/2 to the x over here. So we can just make a table anytime we're not sure what something looks like, although we should have some idea in our head of what this looks like from the work that we've already done with exponentials. So let's just start, I don't know, let's do -4. Okay, so we have a whole bunch of options here. If I plug in -4, I get 2 to the -4, which is the same as 1 over 2 to the 4. And 2 to the 4 is 16. That's 2 times 2 times 2 times 2. So 1/16 is what I'm getting. If I do 2 to the -3, I get 1 over 2 cubed, which is 1/8. If I do 2 to the -2, I get 1 over 2 squared, which is 1/4. And at some point here, maybe we recognize what we were working on yesterday. There's a definite pattern here. To get from 1/16 to 1/8, I multiply by 2. 1/8 to 1/4, I multiply by 2. And this should continue. This is 2 to the x, so the base is 2, which means we have repeated multiplication by 2, repeated doubling. So 1/4, next would be 1/2. 1/2 times 2 is 1. 1 times 2 is 2, 2 times 2 is 4, and then 8, and then 16. So if we start plotting these points, we're starting at -4, 1/16, very, very close to the x-axis. -3, 1/8, still pretty darn close to the x-axis. -2, 1/4. -1, 1/2. 0, 1. 1, 2, 2, 4, 3, 8, and then it falls off of our graph. 4/16 is a little too high. But I think this is starting to get us a pretty good pattern, and if you're not convinced, play around with some more numbers. But basically, the more negative the power, the closer to 0 our y value gets, and the more positive the power, the more our y value skyrockets. On the left side, that approaching 0, that is asymptotic behavior. So it does have a horizontal asymptote at y equals 0. And it does have a y-intercept at 0, 1. And then we have all the other points that I could want just by plugging into the function. So that is what we looked at already as a fairly typical exponential growth shape. Based on the playing around we did in our first look at exponential functions, we really kind of focused on the quadrant 1 stuff, so you may not have noticed that horizontal asymptote. Okay, if we do the same thing for 1/2 to the x, here, we'll just line it up right next to it. So this was 2 to the x, and now we're going to do 1/2 to the x. Okay, so if we do 1/2 to the -4, that's 1 over 1/2 to the 4th, and you can follow that through But I hope you will believe that that ends up just being 2 to the 4. So we flip the 1/2 over to get rid of the negative exponent. We just get 2 to the 4, which is 16. If we do 1/2 to the negative 3, we end up with 2 cubed, which is 8. And 1/2 to the negative 2, we'd end up with 2 squared, which is 4. And hopefully we're spotting that same pattern showing up where we're multiplying by that base of 1/2 over and over and over again. So 1/2 of 4 is 2, 1/2 of 2 is 1, 1/2 of 1 is 1/2, and then 1/4, and then 1/8, and 1/16. So we see a lot of those same values happening because of the way 1/2 flips and becomes 2. So over here on the graph, again, the 16 won't fit, but we can do -3, 8, and then -2, 4, and then -1, 2, 0, 1, 1, 1/2, and then we're down to 1/4, and 1/8, and 1/16. And what we get really kind of looks like a reflection of 2 to the x across the y-axis. And actually it is. If we look at 2 to the negative x, a negative with the x would flip over the y-axis, but that's the same as 1 over 2 to the x. And that's actually the same as 1/2 to the x, because 1 to the x is always 1. So really they are the same thing. So exponential growth and exponential decay are really the same shape, just flipped across the y-axis. So that's a really important thing to realize, is actually it's all one parent shape, but if the base is bigger than 1, you're going to have growth, and if the base is between 0 and 1, you're going to have decay. We don't look at negative bases because we start to get weird domain problems. So you could have a function with a negative base. We just wouldn't categorize it in this family of exponential functions that all have this really nice similar shape. Same problem with a base of 0 or 1. You can make a 0 to the x function or a 1 to the x function, but it won't look like these. So we don't categorize it with the family exponential functions. If we change these to 3 to the x or 1/3 to the x, we would have a similar basic shape, but all the points would tweak a little. So instead of 1, 2, we'd have 1, 3. And instead of -1, 1/2, we'd have -1, 1/3. So what I want you to have in your head is this basic idea that if your base is bigger than 1, it's going to look something like that, exponential growth. And if your base is between 0 and 1, it's going to be exponential decay. I also want you to be aware that they all have a horizontal asymptote at y equals 0. And it's probably handy to realize that they also all have the y-intercept 0, 1. So as soon as we start applying transformations, those things might change, but the parent functions all go through 0, 1, because regardless of what your base is, b to the 0 will be 1. So those are some nice characteristics to keep in mind as you're trying to set up your parent function.